Hello everyone, my name is Yu Hao Huang from the National Taiwan University. I'm today excited to present some recent findings by myself and colleagues regarding the critical role of chiral interlayer exchange in magnetic multilayers, which can assist achieving current-induced field-free switching in perpendicularly magnetized layers. Some of our work has already been published in Physical Review Applied, as shown by the QR code here. I'll begin by introducing the interlayer-Chalositsky-Moller interaction, which is essential for research on achieving field-free switching in perpendicularly magnetized layers. I'll cover how to generate IDMI during sample growth and capture its effective field, known as HDMI, through field scan measurements. We'll confirm the reciprocity of IDMI with longitudinal and polar magneto-optical co-effect. Then, using HDMI, we'll demonstrate how to switch a PMA magnetization in a field-free manner. Finally, we investigate various mechanisms that can arise due to symmetry breaking, such as the tilted PMA anisotropy and exotic spin currents. And we will then compare the importance in field-free switching. Then there's our conclusion. Now, for the emergence of DMI, two factors are required: a sizable spin-orbit coupling and invergent symmetry breaking. For instance, a high interfacial DMI is often observed at the platinum-cobalt interface. Importantly, recent theoretical calculations have extended DMI to a 3D texture, where a symmetric exchange interaction occurs between two discrete magnetic layers. This is achieved by introducing an additional implant symmetry breaking into the structure. In practice, we induced implant symmetry breaking through wedge or oblique deposition. The disabled sample rotor created either a thickness gradient or some kind of columnar structure due to templating effect. We then investigated the macroscopic phenomenon resulting from the interlayer DMI. By observing the basic form of antisymmetric exchange and taking analogy with the Zeeman energy, we deduced the effective fields experienced by the individual layers, which depends on the other magnetization's direction, demonstrating the reciprocity of the interaction. Note that the DMI's characteristic D vector is well defined. It governs both strength and direction of the interlayer DMI. The IDMI's comparison with a conventional interfacial DMI is provided here. In our experiments, the sample structure consists of a PD-core BT PMA multilayer stacked on top of an implant magnetized cobalt-boron layer. The sample rotation was disabled. Thus, the fixed direction of the cobalt-boron atom flow determines the symmetry breaking direction. The D vector must be perpendicular to the mirror plane parallel to the cobalt-boron flow to satisfy IDMI's mirror symmetry. To capture HDMI, we devised a field scan procedure where a constant implant field with a specific phi direction fixes the IMA magnetization while scanning the HC field to capture the PMA hysteresis. The results show a indeed sizable shift in the switching boundaries called, we termed it edge offset, which heavily depends on the phi direction and do not exist in control samples. Furthermore, a sinusoidal form of edge offset with regard to phi clearly shows antisymmetric behavior. The sinusoidal fitting suggests a HDMI of 37 oersted, and the angle dependence confirms that the D vector is indeed orthogonal to the symmetry breaking direction. Since IDMI is reciprocal, an effective field is also exerted on the IMA layer. In the first case, for a modest HDMI, when HDMI cannot overcome PMA's coercive field, in this case, we initialize the PMA magnetization toward either positive or negative Z directions. Then we test the IMA's response via LMOC measurement. And as seen in the implant field scan, the IMA hysteresis loops are significantly shifted to either side, depending on the PMA initialization. This proves antisymmetric effective field to exist in the IMA magnetization as well. The DMI interactions energy density, by individually considering either the IMA or PMA magnetization, they show good mutual agreement. And furthermore, in the second scenario, where the HDMI actually exceeds its PMA coercive field. The implant field sweep will result in magnetizations switching coherently, as evident in the P-mode measurement. Not only that, the PMA magnetizations switching polarity is determined by the implant field scan sequence. This coherent switching behavior is instrumental in achieving field-free switching. We now explain how IDMI assists field-free switching. The IDMI's D-vector separates the XY plane into two regions, let's say when the D-vector lies towards the minus X direction. When the IMA magnetization lies within the first and second quadrants, the HDMI is positive, and when IMI lies within the third and fourth quadrant, they are negative. Under sizable spin current, and implant magnetization switches follow the type Y scheme. For example, the MIMA in this 45-degree device can be switched back and forth between these two regions during current-induced switching. And how MIMA traverses the XY plane determines the corresponding HDMI, and thus the PMA's switching polarity. As a consequence, the 135-degree device's field-free switching should have an opposite polarity to the 45-degree device due to the orthogonal geometry. In short, relying on HDMI, which changes sign depending on the direction of the IMA magnetization, field-free switching should be achieved. The current-induced magnetization switching measurements are performed at a magnet-free probe station. As shown in the blue data set for either the 45 or 135-degree devices, field-free switching for both devices are achieved. We observe that not only is their switching deterministic, they also have opposite polarity, as predicted by our previously explained model. Our model also suggests that the PMA magnetization and IMA magnetization should exhibit coherent switching. And to verify this, additional current scans utilizing the unidirectional magnetoresistance are performed to probe IMA's magnetic states. The IMA switchings are sketched as the red data points in the results below. Indeed, their critical switching currents nicely agrees with their PMA counterparts, directly confirming coherent switching. And we can say that, in a way, the implant behavior is imprinted onto the PMA's magnetization via interlayer DMI. Additionally, note the IMA's switching polarity never changes because the IMA's switching polarity is solely determined by the spin polarization generated from spin-Hall effect, rather than the device geometry in the XY plane. After demonstrating field-free switching, analyses are performed to compare the effect of IDMI to other effects that can occur in symmetry-broken systems. One prominent example is the tilted PMA anisotropy. Here we separately fabricated a series of samples where stacks of PT cobalt multilayers served as the PMA layer and a thick cobalt beam the IMA layer. We choose this multiplicatively stacked PT cobalt multilayer to generate variations in IDMI exchange length and the degree of tilted anisotropy. Previous results on tilted anisotropy has showcased the shift in hysteresis loops to be linear to the external implant field. To separate the two effects' contribution to the hysteresis loop shift, an important trait of IDMI is utilized. The IDMI's effective field actually saturates once the IMA magnetization is fully aligned by an external field. Thus, by considering the tilted anisotropy's contribution to be linear and the HDMI saturation at some edge implant, their individual magnitude can be separated. As seen in Figure B, the saturation occurs at around 100 oersteds. The HDMI actually decreases with increasing n, which may be due to the increase in overall exchange length, while the tilted anisotropy's overall effective field gradually increases with increased stacking. Overall, the exact HDMI magnitude and the ratio of the tilted PMA's effective field with respect to the external field are listed in Figure C and D. We now aim to verify the governing mechanism in assisting field-free switching. The PMA's tilting angle is fitted by treating a shift in the hysteresis loops as the external field's projection onto the PMA's z-axis, which should be slightly tilted towards y-axis due to wedge. The extracted tilting angle shows an increase from 2 to 5 degrees as the repetition n increases from 1 to 4. We then individually tested the field-free switching behaviors. First, it is clear that the IMA normalizations switching are all full switching, as seen from the switching percentages, the only difference being the gradually increasing switching currents due to current shunting. However, the PMA normalizations switching percentage drops significantly, decreasing from more than 70% to 0 in n equals 4. These switching behaviors clearly indicates the dominant role of interlayer DMI due to the following reasons. First, a good agreement between the switching currents confirms the coherent switching scheme of the two mechanizations. And second, the decreasing HDMI when n is increased coincides with the drastic drop in PMA's switching percentage. Third, the trend of the increasing tilting angle is opposite to the trend of the switching percentage. Thus, we can say the tilted PMA anisotropy does not influence the field-free characteristics significantly. We performed a current-induced hysteresis loop shift measurement to see the role SOT plays in field-free switching. The overall loop shift results suggest that regardless of the repetition n, there is no asymmetry in H over I that may have broken the switching symmetry, and the H over I is in itself too small, too low to induce switching. Lastly, we compared different possible mechanisms and their corresponding values in samples with different n. Overall, the IDMI's effective field follows the field-free switching behavior most closely, with other two mechanisms either contribute little or have an opposite trend. Therefore, the dominating role of IDMI in our field-free switching behavior is confirmed. Well, this presentation's conclusions is that through wedge deposition-induced symmetry breaking, interlayer Choleshinski-Mora interaction is generated between separate magnetic layers. The reciprocity of IDMI verified by both PMA and IMA measurements using MOC. Harnessing the IDMI effective field, field-free switching with controllable polarity is achieved. And lastly, confirmed the dominant role of IDMI in such field-free switching and compared to tilted PMA and unconventional spin currents. And lastly, I'd like to thank my advisor, Professor Qifeng Pai, for his supervision, and also my gratitude to co-author Yongchen Li and my lab mates for their contribution. Thanks for listening, and see you.